Hello everyone, in this tutorial I'm going to show you how to simulate a reinforced beam under 3-point bending in Abaqus. So we have a concrete which is reinforced with steel bars. At the bottom we have two fixture, and at the top a projectile. So the material property is going to be a little bit more advanced in comparison to what we have done in the past two examples. So here on the top of the elastic behavior, which is Young modulus and Poisson ratio, we're also going to use the plastic deformation data as well. For concrete, we generally need a more sophisticated model, and I have another tutorial, another course in Udemy, which is more deep into failures in a different type of material such as concrete, metals, composite. So if you want to learn more, as the aim of this tutorial is for you to learn a basic in Abaqus. Once you finish this tutorial, then you can carry on and trying those tutorials to learn more about advanced material properties in Abaqus. So now let's start modeling this 3-point bending in Abaqus. So similar to previous examples, I'm going to start from part, and I'm going to start with beam. So I'm going to call this one beam, and this time our model is going to be in a 3D environment. So I'm going to select 3D, deformable, solid, and extrusion. And again, because the dimensions are going to be in millimeter, I'm going to keep this approximate as 200. So click on continue. And what I'm going to do, I'm going to draw a rectangle from here to here, like this, and I'm going to give a dimension to this one. So from here to here is 200, and from here to here is 10 millimeter. And then cancel this dimension, and I'm happy with the sketch. Click on done, and here's the we need to give the extrusion. So basically currently it's 20. I'm going to make this one 25. So that's going to be my beam. So I have the first one. The second one, it's going to be the fixture. So I'm going to create a, call it fixture, and so this is going to be 3D, but it's going to be discrete rigid. So which means that I'm going to consider this as a rigid body. So I'm not expecting any sort of deformation in this fixture, because obviously I know that the beam is weaker than a fixture. For instance, in this case, beam is made out of concrete and the fixture are steel. So because in real life I know that there's not going to be any sort of deformation on my fixture when I'm going to do a test in a real life. So I'm going to consider it as a discrete rigid. This will significantly reduce a computational time. So I'm going to click on continue, and for this one I'm going to select on a circle, draw a circle like this, and I'm going to just select from the side. I'm going to go down like this, go up, and I'm going to give a dimension now to this one. So let's keep this one at 5, and from here to here it's going to be 30, and I'm going to use this auto trim, and I'm gonna get rid of these ones and cancel the dimension, click on done, and again make this one 25. Okay, so we have this one, but this one is solid. So if I click on this one, you see that the inside is full. And if you remember in the parts section, we said that you cannot have a solid discrete, so we have to transfer this into a shell. And in order to do that, I can select on this one and go at the end here. It creates shell from solid. So if I click on this, click on done and done, and if I select the section cut again from top, you'll see that the inside is empty. So this is now ready to be used as a rigid fixture. So again, because this is fixture, this is a rigid body, then we have to define a reference point. Otherwise we won't be able to fix these bodies. In order to do that, we can go to tools and from here reference point, and we can select any point, but generally I select the one in the middle. So which means that if I fix this point, it's going to apply that boundary condition to all these body. Or if I apply displacement, like let's say 1 millimeter in y direction, all this rigid body is going to move. So basically all this rigid body gets its boundary condition from this reference point. Okay, so now let's change this one. I'm going to make this one fixture bottom, which is, this is going to be the two fixture that is going to go, it's going to be at the bottom, and I'm going to create another copy of this, and I'm going to call this one top. So that's going to be fixture top. Click on OK. And the reason that I've done this is that when you want to apply a displacement to a rigid body, you have to give a mass to that one in a property section, because if you look at this one, you'll see that the bottom one is going to be fixed, but this is going to be like a projector, so it's going to move down and it's going to put a pressure on the beam. And when you have a rigid body and that body is going to move, then you have to give a mass to that one. So that's why I separated this. So I have a fixture at the bottom that I'm going to use it for bottom, and fixture at the top that's in the property section. I'm going to add a mass to only the top one, because the top one is going to move basically. So so I have beam, fixture, bottom and top. Now I'm going to create a reinforcement. I'll call this one RC, and I'm going to use it 3D deformable, and this time wire, and approximate size 200 is fine. Click on continue, and so I'm going to draw a line from here to here, and I'm gonna select this one and make it 200, and then I'm gonna use a linear pattern. Select this one, and first of all I need to find out which one is which direction. So let's reduce this one. So this is the X direction and this is a Y direction, and if I make a space 5 and if I do 4 of them, so it's going to be 1 2 3 4, and so the distance is going to be 20 in total. Click on OK, and then I'm going to draw another line from here to here, and I'm going to make this one 25. Let's just, before doing that, I have to make sure that this is going to be in the middle. So because I know that the distance from here to the middle should be the same from here to here. So what I'm going to do, I'm going to first of all give a dimension from here to this line, and I'm going to make that one 5, and I'm going to give a dimension, the total, I'm going to make this one 25. So now if I do from here to here, you see that that's 5. So sometimes it's important you give the smaller dimension first and then total dimension, because Abaqus is not generally as smart as other CAD software, because I mean you don't have that 0 coordinate that you have in a CAD software that you can use it as a reference point. Unfortunately you don't have it in Abaqus. Either you have to create it using this construction line, or you can use a small dimension to fix it in a correct location and then give the larger dimension basically. So now I'm going to have a distance from here to here. I'm going to call this one 20, and so now as you can see this one moved in comparison to this. So what I can do with that one, I can go to here, and so I have to use a coincident one, but again here I need some sort of construction line. So I'm going to use this one, select this, and I'm going to make that one fix. So I'm going to make this line fix here. Click on OK, and then I'm going to say this line going to go on this, and oh, I was on the wrong one, so let me just Ctrl Z this one. So I'm going to go coincident. I'm going to set this one on this line, this one on this line, and this one on this line. So basically now all of them are 20 millimeter away from this construction line. You could actually give a dimension for each of them individually, but I just wanted to show you a different way of doing this. So now we have this one, and now again I'm going to use this linear pattern. I'm going to select on this, click on done, and so this time I'm gonna use the top one, which is the X, and I'm gonna make this one 1, and the direction is in the wrong direction, so I'm gonna increase this one and click on OK. 9 of them, click on OK. So now I have the reinforced beam. Click on OK. So this is my basically RC. I got this reinforcement for the beam. So we have the beam, fixture, and reinforcement. Now I can go to property section. Now I have to create a property for each of these model. So first of all, let's start with steel. So now I'm gonna click on create material, and from here I'm gonna call this one steel, and go to mechanical elasticity elastic. So this is going to be gigapascal, but my unit is millimeter, so I have to write this in megapascal. So that's going to be 210,000 megapascal. So I need 40, 1, 2, 3, 4, and Poisson ratio, let's put this one 0.3. And then I'm going to go here, plasticity plastic, and I'm going to give a plastic deformation. So the yield is 251, and the plastic strain is going to be 0, and then after that it will start 264, 0.024, 295, 0.049, 316, 0.074, 326, 0.099, 334. Yes, so this is going to be 0.099, and 334, 0.124, 336, 0.149. So 339 here. So in order to quickly jump to the next one, I'll just press tab button on the keyboard, 0.174. So I'm done with this. So this is still, click on OK. I'm gonna go to beam, RC, and this RC basically it's gonna be in a 2D way. It's similar to the stadium roof that we made. So we have to create a profile for it. So I'm gonna go to a profile, and I'm gonna select the circular, click on continue, and I'm gonna say that the diameter it's 1 millimeter, and click on OK. So now if I go to create section and beam and call this one steel, click on continue, and I have the profile here, I have a steel here, click on OK, and I can assign this to this RC, click on OK and OK. Next step is to assign the beam orientation. So go from the assign tab, beam section orientation, select all of these, click on OK. I think that I cannot select the OK here. Maybe I have to make this one bigger. So click on done, yeah, and then press another one, enter. Just check the tangent and normal direction. So you can see 1 and 2 are normal and tangent, they're all in the correct direction. Generally Abaqus get this one right, except that if you have a very complex geometry, or you made a mistake somewhere in drawings, or you imported your CAD file, but generally this Abaqus get this one right. So click on OK, and if I go to a view and from play stack plot option, oh sorry, again from part display option and click on render beam, click on apply, and that's going to be our reinforcement that we're going to place it in a concrete beam. Next step is to make a property for a concrete. Okay, so now I'm going to make material properties for concrete. So I'm going to go to beam, create material, type concrete at the top. So that's going to be mechanical elasticity elastic. And the Young modulus is 51 gigapascal, but we have to write it in a megapascal form because we are using a millimeter SI system. And for Poisson ratio 0.3. For plasticity, generally in Abaqus we have concrete damage plasticity, concrete smear cracking, and also there are other plastic behavior properties that we can actually define using a subroutine in Abaqus. But in this tutorial we're going to keep it simple because the aim of this course is just for beginners to understand the software. But there are loads of tutorials in Abaqus which is like a advanced or intermediate level in Udemy website or other website. Myself has 2 courses that one of them is dedicated to structural engineering, which I talk more about it, failure in concrete and metals. And if you're interested, you can look into you can find that in my profile in Udemy, and if you're interested to know more about concrete, you can check that tutorial. So let's continue with this one. Click on OK, and now we have to create a section. So I'm going to call this one concrete homogeneous, continue, and I'm going to consider this concrete. Click on OK, and then I'm going to assign this one to this part. So now I have a concrete and a beam, and also I have the material properties for reinforcements. I said we have to apply a mass to this one, so go at the top, special, inertia, create, and we have a point mass inertia. Click on continue and click on this one, done. So now here I have to give a mass. Okay, you have to make sure that again you have to be careful of the unit system. If you remember the unit system that we had in Abaqus, if I showed you here, the SI unit system for millimeter is a ton, so the mass comes as a ton. And let's say, imagine if I want to say, oh yeah, this is a 1 kilogram, then I cannot write 1, so I have to write it in a ton unit system, so 0.001 ton. Click on OK. So I have a mass for this one as well. So that's for fixture top, and we don't have to do anything for fixture bottom because it's completely fixed. So now we're going to go to assembly section. First I'm going to enter a beam, and I'm going to bring it as a dependent, and the next one is going to be fixture at the bottom, and I'm going to activate auto offset. It's going to go on the side. So as I showed you in the basic videos in the assembly section, there are different ways of creating a 3-point bending. The easiest way is to basically partition the location that you want to have your fixture there. So I can do that by going back to part, go to beam, and I'm going to create a datum plane. Select this one, enter a value, flip this, click on OK, make it 40. So that's going to go here. I'm happy with that. Now I'm going to select this face again, enter a value, OK, and this time it's going to be in the middle, 100. And the next one, I'm going to select this one, enter a value. It's going to be 40 from the other side, but from here it's going to be 160 because the total length of the beam is 200. So now I can create a partition using a partition with a datum plane. So from here, create partition, use a datum plane. First I'm gonna use this one in the middle, create partition, then select this side, click on done, select this, create partition, select this, done, this one, create partition. And what I'm gonna do now, I'm done with this part, so I'm gonna go to assembly, So as you can see, I have the correct location for each of these. So first I'm going to start with this one, so I'm going to select the top and here, and again another one, fixture bottom, so that is going to go here to here, and the next one is going to be fixture top, and I have to rotate this one because in the wrong direction, so I'm going to click on this, done. So I have to rotate it basically along a z-axis. So first one 0 0 0 0 0 1, and I'm going to rotate it 180 degree. So as you can see now is at the top there. So now what I'm going to do, I'm going to move this one to the correct location. Right, now the aim is to basically add the reinforcement to this beam that we have here. So in order to put the reinforcement that we created, we need to do a couple of extra steps. So first of all, I'm gonna add the RC, so it's going to be dependent mesh again. Click on OK. And what I'm gonna do, from the top here, I can activate or deactivate the beam. So first of all, I'm gonna deactivate it so I can actually select the node easier. And as you can see, the reinforcement is not in the correct direction, so I have to rotate this one. So I'm gonna select this, click on done. So the first one is going to be 0 0 0, and the rotation is going to be along the x-axis, so 1 0 0, and I'm going to rotate it 90 degree, so click on OK. And the next step is to place this one in the correct location. So I want to have this reinforcement in the middle of the beam, so if I click on here and this one, and it can go in the middle of the beam here. As you can see, I cannot really see the reinforcement anymore. In order to fix this one, I'm gonna activate the transparency so I can see the inside of the beam, and also I'm gonna change the filter. So the filter is gonna be on a part, so each individual part will have its own color. So as you can see, we have red, green and white, and if you want to change that, you can go click on the here color code and change the color based on the part that you have. So now I can move this one to the right side. So as you can see, a little bit of the beam is outside, so I'm going to use a translate, select this, click on done, and the first one is going to be 0 0 0. Then I'm going to move this one in a minus z direction, so it's going to be 0 0 and minus 5, and click on yes and click on done. So as you can see, the reinforcement is now in the middle of the beam. So if you go to view assembly display option and activate the beam and apply that, you'll see that now we have this concrete beam which is reinforced in the inside of it. So currently Abaqus actually doesn't know that your beam is reinforced. So I know that you put the reinforcement in the middle of the beam, but if you have direct force, Abaqus doesn't really know that you put this one in the middle, and probably you're going to get a convergence problem. So how are we going to solve this? We're going to solve this in the interaction section, but before doing the interaction, I'm going to create a step. For this one, so create a step, and it's going to be static. Click on continue, non-linear, make this one 10,000, this E-5, and make this one 15. So I've explained this one properly in the step section. If you haven't watched that video, please do watch it if you want to know more about what is the best value to put for initial minimum in this section. So click on OK and then go to interaction. So there are different ways of defining a contact between a fixture and the beam. So the first one is defining a surface-surface contact, and the second one is a general contact. Basically, once you define a general contact, that means that you define a Abaqus will basically define a contact between anything that you assemble. For instance, the fixture that you have the contact between these two and these two and these two. Okay. And again, if you want to know more about these ones in Abaqus, please watch the video in the basic section that I explain the interaction fully there. And here I'm going to just demonstrate how to make a 3D beam, and I'm not going to go into details about this one. So before creating a general contact I'm going to use for this specific tutorial, I have to create a properties. So basically I need to say what is actually the interface properties between this surface and that surface, and I can do that by creating a contact interface properties, and I'm going to use a mechanical tangential behavior. I can consider it as a frictionless, I can consider it as a penalty, so I can define the friction of coefficient. It really depends on experiment that you do. If you think that you have some sort of friction, you can put a value here, but what I saw in the literature, normally the value between 1.1 to 1.2 is the acceptable value for the friction of coefficient. For this test I'm going to consider it as a frictionless, and I'm also going to consider normal behavior, which the pressure on overclose is going to be a hard contact. Again, if you want to know more about this, please watch that video in the basic section. So now click on OK. Now we have a contact, we define the contact, basically interface. So what we need to do next step is to generate that contact. So I'm going to go to general contact, and in the initial step click on continue, and for the global property assignment I'm going to select the first one and include the surface pair. I'm going to consider all surfaces and click on OK. So now I have basically a contact in the between fixtures and the beam. So the next step is to basically define this reinforced inside the concrete beam. So as I mentioned, Abaqus doesn't really know that you put something in there until you define that contact. In order to do that, you can go to create constraint and use the embedded region. Okay, so if I select the embedded region, then I can select the embedded region and also the host for it. So before doing that, I have to create some sort of set, because for me to select the inside of that beam, which is the reinforced, it's difficult to do it like here. So what I have to do, I have to basically get rid of this corner and then select the reinforcement. To make your life easier for us, especially for complex geometries, I can create a set, so it would be I can access the reinforcement much easier. So you have to go back to part, select the reinforcement, tools, set, create, and I'm going to call this one RC embedded, and click on continue and select everything and click on done, and then go to beam. Again the same thing, tools, set, create, and call this one region and embedded, and click on continue, and again select everything, click on done. So if I go back to interaction, and if I click on create constraint and embedded region, click on continue, then I can go to the sets here, and from here I can actually find out the one that I created. So this is the one I created. So it's selected embedded region set from the dialog. So I'm going to select this one, and if you, from the bottom, if you activate this one, you can actually see what you are selecting. Click on continue, and the next one is to select the method for the host region. So basically you select the region, not the whole model. And obviously if you didn't have a fixture, you can just select the whole model, but I just want it to be in the beam. So I'm going to select the region, and from here I can select these, select region embedded. So again, activate the highlight so you can see what you're selecting. Click on continue, and keep the parameter as it is. Click on continue. So as you can see, now I defined basically a reinforcement inside this concrete beam. Okay, in this section I'm going to show you how to apply boundary condition on this 3-point bending. So first of all, we need to fix the bottom one. So click on boundary condition and go to the first one. I'm gonna select this one, hold the shift, select the other one, and click on done, and apply a fix in all directions. Click on OK. Then we have to apply a displacement to the top one. So again, go to here, displacement, click on OK, select on this one, click on done, and what we do, we basically make everything 0 because this is the initial step. Then we we click on the boundary condition manager, and we click on the propagated. So it's going to be a step 1 that in initial step everything is fixed, but in the propagated section, then we click on edit, and we deactivate. So in here we can change this one. So basically we can say this is so -5. Yeah, click on OK. So we have a displacement toward the down, and the next step is basically fixing a beam. So in real life, when you do this type of test, you normally have some sort of preload on your sample. So the top fixture hold the sample properly. So when you start a test, your sample won't slide to in a Z or X axis. However, when you do a simulation, if you don't fix your beam, what will happen once you apply the force, the initial contact will cause the beam to slide to X or Z direction. So that's why we try to fix the beam only in a X and Z direction, so the beam doesn't move. Otherwise, if you don't do that, you will have a convergence issue. So what I'm going to do, I'm going to go on a displacement that can be on a step 1, and select this line at the bottom, click on OK, and then we select on this one, rotation, and it can only move to a Y direction. So by applying this setting, basically will stop a beam from moving to Z or X axis. Click on OK. So now we are done with a boundary condition. Next step is a mesh, and then after that we can run a simulation. So now from the top, go to mesh section. So from the object we have to select part, because in the assembly section we selected a dependent, so it's going to be mesh on a part. So I'm going to go to mesh and part. So we have to apply a mesh individually. As you can see, our beam is colored as green, so it's going to be structured mesh. So if I go here, seed edges, select everything, click on done, and select the approximate size 2, and I think this is fine for this example, and click on OK, assign a mesh, say yes, and then I'm going to do the same for fixture. As you can see, this one, the element for mesh control is on F3. So if I select everything and click on done, I can select the structural shape, If I go for a structure, you'll see that I can only apply a structure on the side, not on here, because the front face is a combination of two different shapes, which is a semicircle and a rectangle. In order to apply a structure mesh to this one, you should actually partition this one from this edge, and then you would be able to apply a structure mesh. But for this example, we are happy with this one, so the software will say that it's not, the quality won't be good, so I'm happy with that to get rid of that and click on OK. Then I'm going to assign a mesh to this one, and let's say 2 is okay, apply it and assign a mesh, say yes. I'm going to do the same for the bottom one, so first of all I'm gonna change this one to structure, say yes, click on OK and assign a mesh for this one. Again, 2mm is okay, assign a mesh, yes. And the last one is gonna be reinforcement, so I'm gonna assign a mesh to this one as well, 2mm, apply it, OK, and select everything. So now I have a mesh on my reinforced beam, and if I activate this one, we can see the inside of our geometry. So we are done with the mesh. Now we can run a simulation. Okay, so now we are done with everything. I'm gonna create a new job, and I'm gonna call this one 3-point bending, and I'm gonna call it number 2. Click on OK, done, and I'm gonna submit the job, and also I can monitor that if everything is okay in this job. So I can go on the monitor and see everything is okay. So this is completed, so now we have to just wait for a result to appear. We don't have any error in the setup, so it's just a matter of time until we get a result. Okay, now the job is done after 9 increments, so we can see the result by click on the results section, and if I click on this one, I will see the deformation in the beam. We can activate the transparency and see the beam inside. So let's just go to view ODB display and render. You would notice that we cannot actually see the stress on the beam. Even if I deactivate, put this one on edge, you see that the result will only appear on the concrete beam, not the steel reinforcement. And this is because for reinforcement we are using a wire, and in the other one we are using a solid, and Abaqus wouldn't show the result both of them at the same time. What we have to do, we have to basically activate the result one by one. By first of all, let's get rid of the so I'm gonna cancel this one, so I'm gonna select the part instance, get rid of these, get rid of this one, and also this one. When I say get rid of, that means that I'm temporarily getting rid of this, and if I click on OK, then I would be able to see the stress on the bar. So again, you won't be able to see the stress result at the same time when you are using a wire and a solid, or even a shell. It doesn't matter. You cannot use the when the geometries, they don't use the same structure. Either you have to be all solid to be able to then you would be able to see them, see the result. Otherwise you have to see the result individually. So for instance, in this case we can see the stress value, which is like 92.16 megapascal on a steel ball, way below a yield. And also I can see the displacement as well that we have here. So it's around 4.98 millimeter. If you remember, we applied 5 millimeter on this one, so we have 4.98 millimeter displacement on the bar. Now I can what I can do, I can bring back everything, and I can see the displacement value. So on the here the displacement is 5 millimeter, and we can see the stress value. So the stress value here is quite high, 822. So this is way above the way above the plastic yield stress of the concrete. I think if you remember, it was around 15. And if you try to put this plastic information data in the material section, you would see that the software won't be able to converge this one. So that's why we are using a more advanced plastic behavior properties in Abaqus to simulate the failure or plastic deformation in concrete. So that's basically everything in this tutorial. You learn how to use a combination of solid parts and wire, and how to use the embedded region in interaction for reinforcement, and how to basically plot these ones separately in Abaqus. I hope you enjoyed this tutorial, and I hope you find it useful. I hope to see you in the next video. Thank you so much for watching.